Hi, everyone. My name is Andres Freund. I work for EnterpriseDB. I'm a PostgreSQL developer and committer, and I want to talk about the new just-in-time compilation in PostgreSQL 11 and where it works, where it doesn't work, and thus how you can use it. It's worthwhile to note while I work for EnterpriseDB now, a good chunk of the work that I'm talking about has been done while I was working at Citus Data. So I think they deserve some thanks for that too. If you have any questions while I'm talking, please just try to raise your hand. I think I probably have enough slack to just answer them. If not, then I'll just stop answering. I'm not going to go into too much like benchmarking details today, because I think that's just a different talk. I want to explain to you when it will be likely useful for your use case and how you can figure that out. And I'm also not going to go into too much low-level detail about how exactly the just-in-time compilation works, because I think that's also a different talk, and I just can't do everything in one talk. So why is just-in-time compilation an interesting thing to do in a database? I think that's a pretty crucial question if you want to do something, a large project like this. So as an example, and I'm going to use this repeatedly, this query, I'm only going to use this query for the rest of the talk, because then we don't have to go through what the query does every time. This is a relatively simple analytics query. It's taken out of the TPCH benchmark. It's the query 1 in there. And it's basically just doing a bunch of aggregates over one table, has a filter on that table, and then groups by 2 columns. And if you look at how that query is executed, and these numbers are from my laptop while on battery power, so the numbers here are not really representative. You can see that if you are familiar, who is familiar with explain plans and who is not, or who is not familiar with explain plans? Okay, cool. Sorry. What this explain plan shows is that we have a plan that takes about 30 seconds to execute the query. And because I've enabled the track I/O timing setting, you can see that in here, this query at the moment takes about 6 seconds just alone to do I/O. And the rest of the time is spent first doing a sequential scan. And that here takes about 13 seconds. And that includes the 6 seconds for doing I/O. And then above that, we have an aggregate that does the aggregation, and that takes most of the rest of the time. So you can say, if you wanted to make this fast, execute faster, there's a few options we have. The first one would be, hey, we can just avoid doing I/O. So if we force this to be cached, the query takes about 26 seconds, and the majority of the time is not done in the sequential scan. That takes about 8 seconds. But in the hash aggregate, which includes those 8 seconds, but in addition to the 8 seconds, it takes another 18 seconds. So we spend a lot of time in the hash aggregate. And at this point, we really can't easily make this query plan faster. For this, the sequential scan is right. An index would only make it slower. What we could do is look at the profile and say, OK, at the moment, most of the time is spent doing expression evaluation. That is evaluating the aggregate and the filter and deforming the tuple. What deforming the tuple is converting the representation of like tuples, rows that are the representation on disk or in memory, which is relatively compact, into something that can be accessed more efficiently and more conveniently. So that's where most of the time goes. So how could we try to get something like this faster? What we could do is to do more micro-optimizations in Postgres. And we've done a lot of that in PostgreSQL 10 and 11. This query before PostgreSQL 10 took nearly twice as long, or 1.8 times as long. So there was quite a bit to be done there. But there's no easy ways to go much faster. There's some smaller things we can do, but it doesn't get us much further. The biggest approach which we obviously could take is to use parallelism. Since PostgreSQL 9.6, and then especially since 10, we have a lot. We can just parallelize this query. If you just enabled parallelism for this query, which I had intentionally disabled, you get nearly linear scalability to up to like 8 to 10 cores. Like with 8 cores, you get like 7.2x performance. That's pretty good. But on the other hand, that also uses more resources. So if you are in a workload where you have a lot of things running at the same time, you can't just add parallelism forever because you might not have the resources to do all that. So that doesn't potentially help for some workloads, but doesn't necessarily help for other workloads. Another approach would be, hey, we can just use more than one computer and accelerate it by farming out the work to multiple nodes. That has the same resource usage type problem, and there's actually no good in-core solution to do that kind of parallel computing across multiple nodes. There's various forks of Postgres, there's various extensions, but in-core there's no good way to do that. Another approach would be to say, we use a columnar store and use vectorized execution or something. This kind of query actually can be done quite a bit faster if you use something like that. But again, there's unfortunately in PostgreSQL core no very good, or in Postgres core there's nothing that allows to do that, and there's a few extensions that kind of get added, but are not perfect. There's CytosDBs, CytosDatas, CStore FDW, but that mostly addresses the compactness, doesn't really make the query that much faster. And also, using columnar stores is not necessarily good if you have a workload that consists out of both analytics queries and some transactional workloads. And it's pretty common these days to want hybrid analytics and transactional workloads at the same time in the same database. And that's just not very suitable for columnar stores. So what can we do? The solution I was taking is that we want to do just-in-time compilation. What is just-in-time compilation? To quote Wikipedia, just-in-time compilation is a way of executing computer code that involves compilation during execution of a program at runtime rather than prior to execution. In this case, the program that we are executing is basically the query plan, or parts of the query plan. Normally, we do that in an interpreted form. We have computer code that executes this virtual program for the query plan, and that then yields the results you want to have from the select, or whatever type of query. And if you've seen the profile order that I briefly showed, you could see that most of the time was spent in a function called exec_exper_interp, which just means evaluate expressions using an interpreter. And that's most of where most of the time went. It's also what we would want to make faster the most. And the benefit of doing just-in-time compilation is precisely that you can take interpreted code and change it into native code. And that removes all the overhead of doing interpretation. There's further benefits to doing this type of just-in-time compilation, because if you have an optimizing compiler, that can also pre-evaluate parts of the program and get better performance that way. And you probably have heard of usage of just-in-time compilation from a lot of other use cases. For example, one common case is in browsers, the JavaScript that you have these days. If the JavaScript is like a loop or something in JavaScript is executed multiple times, the browser will automatically convert that into native code, yielding in fast execution. Without that, none of the modern JavaScript frameworks would actually be usable for the complex applications we have today. Another, and probably the oldest really well-known case, is Java. When you compile Java with a normal Java compiler, it doesn't actually produce code that is natively executable. It produces bytecode that is targeted to the Java virtual machine. But if you just use the bytecode to execution, that's actually too slow for a lot of types of application. So instead, when the Java virtual machine detects, hey, this loop is actually entered, like a couple times, then it also turns that into native code to yield better speed-ups. And it's interesting that with just-in-time compilation, you can often actually have better performance than if you did ahead of time compilation, because you have more information about what exactly to optimize for. So how does just-in-time compilation, how did we integrate that into Postgres? We use LLVM to do the bulk of the work in Postgres. LLVM is a compiler framework. You might have heard of it, used for the Swift compiler, for the Swift language by Apple. It's backing the C-lang compiler, if you ever used C, and on various platforms. And we decided to use that just because we didn't want to do all the work ourselves, and it was the most portable framework that we could find, I could find. At this point, it's an optional feature in Postgres. You can build Postgres without any dependency on LLVM, because LLVM is a really large project. We didn't want to make it impossible to compile Postgres without that. You have to enable it at compile time, but you can install, like if you use a packaging system, you can install the LLVM support separately from the main installation. I'll have references how to exactly do this later. And at this point, the just-in-time compilation does not work on Windows. There's no fundamental reason for that. I just ran out of time to do that at the end of the PostgreSQL 11 release cycle. And I don't normally personally use Windows, so it would have been a bit harder to do myself. If you do compile Postgres manually using the Ming GW, I don't know how to pronounce this, you can actually make it work. But if you compile Postgres with Visual Studio, which most of the distributions for Windows do, there's no just-in-time compilation support at this point.
Question. If you're using Linux, suppose you're using Debian packages, is available?
Yes, I'll have a reference where it's available later. As I said, you can install it separately, so you need to be able to test whether it's installed. What you can do is you can set the JIT equals on parameter, or it's also at the moment defaulting to on, and then you can call the select pgjit available function, and it will either return false or true, or in some very rare corner cases, it will return an error because installation was screwed up in some weird way. If you wanted, the JIT support in Postgres is extensible. You could replace the LLVM dependency with a dependency on GCC and libjit or whatever you want to do, or just do it from scratch. You would have to write a fair bit of code, but you could replace it at runtime and just set that GUC to something else. So what can just-in-time compilation do? And I'll admit that my graphics skills here are not exactly perfect. If you look at the query, I've basically tried to show which parts of the query are just-in-time compiled, and the list at the bottom is basically in what happens in which order. The first thing, when you look at the way the query plan earlier worked, was that we do a sequential scan on the line item table. It's just-in-time compiled there is the deforming of the line item table into this more accessible form, and then the predicate evaluation here, that says the where clause, gets turned into a native function, and that makes it faster. And the way it happens to work, those two get turned into a single function that gets executed. And then the next thing is that we have a hash aggregate on top of that. And for a hash aggregate, what you have to do is you have a hash table that is keyed by the grouping columns, and then when inside the grouping column, you then have to check, hey, is the element that I found that I want to aggregate together with actually a match, or is it just a hash collision? And for that, you have to compare the columns in the hash table with the columns outside of the new tuple, and that's also now just-in-time compiled. And after that comes the biggest benefit of just-in-time compilation, and that is that we have to evaluate both the aggregate input, like the columns that are arguments to the aggregates, and then the aggregate transition function. In Postgres, all aggregates are extensible. That is, you can define your own sum functions for new data types. And the existing aggregates are all defined using basically the same mechanism. That is, if you implement a sum that's basically implemented internally as a function that has a transition value, and then whenever you get a new input aggregate, it just increments the value of that transition function. And the just-in-time compiled function evaluates all the inputs to the aggregate and invokes the transition function. And as if you aggregate a lot of data, especially if you aggregate that to fewer rows, that's where most of the time goes. If you remember the query I had as an example earlier, that showed that we spent 8 seconds doing the sequential scan and 26 seconds, including those 8 seconds, doing the aggregation. So the aggregation itself took roughly 18 seconds. So, and that was nearly all CPU time. And then once we've done all that, the result of the select list, which is just two normal columns, and the result of a bunch of aggregates, and if you had any other type of expressions, are evaluated as a separate just-in-time compiled function. You can control these with a bunch of settings. The basic what you can do is you can just disable just-in-time compilation. There's a setting which is just JIT, and you can set it to on and off. At the moment, JIT defaults to on, and that's in beta 3. We are about to discuss whether we want to enable that by default in Postgres 11 or whether we want to disable that by default in Postgres 11, because it's a new feature. There's some weaknesses, which I will talk about in a bit. So we don't know yet whether we will enable it by default. So nothing will be done without that set. If you have set it to on, then we will do expression compilation. Separately from that, there's a setting that controls whether we do just-in-time compilation for tuple deforming. That will default to on, but you can disable it set it to off, mostly for experimentation. I don't think will be a lot of reason to change that ever in practice. And then there is a third step, and that's a very important one. LVM, the compiler framework, has a lot of optimization steps. It can make the program that is to be executed a lot faster, but that costs actually time. So one thing that you can control, but what we do during just-in-time compilation, we optimize the generated program. And then there's one last step, and that's that we allow to inline functions or operators that are part of the SQL. In Postgres, all functions and operators are extensible, and extensions can define new operators and functions, and that extensibility has some price. And the inlining for just-in-time compilation allows to remove all that overhead, or in theory at least. It's worthwhile to note that you can do this just-in-time compilation inlining even if you use extensions, because extension can register the code that they want to be inlined. So one interesting part, obviously, is what does it help? If you look at the performance for just-in-time compilation of this query that I showed earlier, the TPCH-Q1, this time this is not executed on my laptop, but on a larger machine. It's on TPCH scale 100, which is roughly 100 gigabyte of data. And this machine, there's enough memory to fit all of that in memory. So what you can see is that without just-in-time compilation, the query takes about 50 seconds. And with just-in-time compilation, it takes about 25 seconds. And then here I've shown the degree of parallelism. And you can see that even with relatively large amounts of parallelism, we still see quite a bit of benefit. You will notice that the factor between the just-in-time compiled version and the non-just-in-time compiled version reduces a bit with time, and that's because there's some part of work that is basically done independent, like that's not parallelizable, and just-in-time compilation doesn't help with the non-parallelizable part, and just-in-time compilation has some innate overhead. The next question is, why wouldn't you not always do just-in-time compilation? And the reason for that is the idea of just-in-time compilation is basically you have query execution, and you want to make that faster. So you do additional work at the beginning of and then hope that you do the just-in-time compiled version of the query is actually faster. But if you're unlucky and do it in the wrong situation, you can end up with the following scenario. You can end up doing just-in-time compilation, and the just-in-time compilation takes time, but it takes more time than the just-in-time compilation then actually saves, which means you can end up using more time in total than if you didn't have done just-in-time compilation. Which means we have to have logic to decide when to do just-in-time compilation and when not to.
Can JIT code be cached, or is it always?
2 slides, or 3. Not yet. So at the moment, the planning for this is very dumb. We just didn't quite know exactly what the best way would be, and we didn't have that much time. I mostly developed this on my own, so there was a limited amount of resources, and it's also not perfectly clear what the best way would be. As I said, the first thing that controls whether just-in-time compilation is done or not is whether the just-in-time compile parameter is on or off. Obviously, if it's off, then the planning is very easy. We just don't do just-in-time compilation. But if it's set to on, what we do is we compare the query, the cost of the query, and I'll explain how you can see that in a sec, with one configuration variable. And that variable is called just-in-time above cost, which basically means if the query is more expensive than that, then do just-in-time compilation. And the default for that is at the moment 100,000. The way you can see whether how expensive a query is you can do explain, or you can do explain analyze and run it. And that will show you at the top a parameter called cost here, and that will have like the cost to return the first row, and then the cost to run the full query. And in this case, we're at 43 million, I think. And so it's very clearly above the cost to do just-in-time compilation, because 43 million obviously is more expensive, higher than 100,000. And that will then do just-in-time compilation, but it will not do optimization, because optimizing the generated program actually takes time. And there's quite a bit of cases where just running the just-in-time compiled program without any expensive optimization still yields in a faster execution than not doing just-in-time compilation. So there's a separate setting that says do just-in-time compilation with optimizations, and that the default for that cost is 500,000. And similarly, the same exists for just-in-time compilation with inlining of the operators. The inlining takes a bit of time because you need to look through, hey, do I have a definition of that operator that I'm going to inline, and needs to do then link that in. And there's a lot of complexity in that, so it does cost something.
Once it's compiled, is it always faster, or is there like a cost of entering and exiting like a context or something?
So there's one bug at the moment where you can get that the just-in-time compiled code is a bit slower if you are between the just-in-time but below the just-in-time optimized cost. But normally the code should always be faster after just-in-time compilation. It's just that the overhead of doing the just-in-time compilation sometimes can be significant, because like LVM just takes its time to do expensive stuff. And all of these you can disable by each of these steps by setting the parameter to -1. So for example, if you wanted to do just-in-time compilation, but you never wanted to do inlining for some reason, you could just say JIT inline above cost to -1, and it will never be used. And the same works for all the other settings. And all of these settings can be controlled by every user. So if you have something like, you know that your application mostly doesn't need just-in-time compilation because it's an OLTP application, but you have a few and you don't want to risk that just-in-time compilation is used in some situations where you don't want to. What you can do is to say, I normally set JIT to off, but for a single query, I set it to on and then run it with that.
Does this compilation and linking happens in the private memory of the backend process or inside the shared memory?
It's in the private memory. And it's also worth noting that at the moment, just-in-time compilation is a whole query decision. What that means is that even if parts of the query are actually not executed that frequently, if we decide the whole query needs to be just-in-time compiled, we just-in-time compile everything therein. There's reasons why that is a good idea, and there's reasons why that is a bad idea, but that's at the moment how it works. And it's also important that in contrast to something like JavaScript, the just-in-time compilation in Postgres is not a tracing just-in-time compiler. The way it works in JavaScript, for example, or in most JavaScript engines, is that if you run a loop like 5 times, then it does just-in-time compilation, but not before that. But it turns out that in Postgres, we have an advantage over something like a JavaScript engine. The JavaScript engine doesn't have like statistics about how likely is it that this query runs for a long time. But in a database, we do have that. And if we instead did the tracing part, so we executed parts of the query to 5 times before we do just-in-time compilation, or a couple hundred times, then we lose performance in those first 100 or how many executions where we don't do just-in-time compilation. So we decided that we wouldn't do the tracing. I had implemented initially with tracing, but it turned out it actually reduced performance quite noticeably. So if you do an explain or explain analyze in this case, what it will now, if you have enabled just-in-time compilation, spit out is something like this. You can see it says now that we do just-in-time compilation. Otherwise, if no just-in-time compilation is done, this block is not present. It will tell you how many functions can be just-in-time compiled as part of the whole query. And functions here can not just be like SQL functions, but it's like how many blocks of code are just-in-time compiled. That can be, for example, a where clause. That can be like a group, like a select list. That can be the arguments to aggregates and so on. And you can see that it tells you a couple numbers. It tells you generation time. And that's the time, how long it took for us to generate the input for the just-in-time compiler. And that's basically transforming the interpreted program into some intermediate language that LLVM understands, and then LLVM generates executable code. The process of turning the intermediate format that we pass to LLVM into executable code, that's emission time, because that also includes making the memory executable. And to go back to that question for a couple minutes ago, that memory where we do all this is all processed local memory at the moment.
You need a subcache.
That's orthogonal. You could do caching and process local memory. No, I think that's actually later, but I think that's a reasonable thing to do. And you can see that it shows you inlining true or false if we didn't do inlining, but this query is expensive enough. And if you only do explain, it will not show you the time, because we don't. If you only explain the query, we don't actually do the overhead. Like, we don't do the inlining, we don't do the optimization, because that would be unnecessary to run the for just explain. We only do that when explain analyze is done. And you can see optimization here, and you can see that the time both for inlining and optimization is actually pretty substantial. We lose a couple hundred milliseconds here to do all this work. So when is just-in-time compilation likely to be useful? I first want to talk about which type of use cases are likely to more likely to benefit, and then I will talk about which type of queries and parts of queries are likely to benefit. In general, you're most likely to see benefits from just-in-time compilation if your workload is mostly CPU bound, because just-in-time compilation doesn't help at all if you do if you're mostly I/O bound or mostly bound by latency of your client sending queries and the database getting and then sending it back to the network. Then that's just-in-time compilation has no chance to actually help with that. Similarly, if you have an OLTP that is transactional workload with a lot of different short queries, just-in-time compilation is not going to help you, because the overhead of doing just-in-time compilation would often be higher than actually running the whole query. And at the same time, the bottleneck is normally for OLTP type queries is not evaluating expensive expressions. It's locking, it's transactional overhead, it's the latency between the client and the server. It's walking through indexes. It's I/O to get the data into memory if your workload is bigger than memory. So just-in-time compilation just doesn't help much there. If your workload is completely I/O bound, just-in-time compilation also doesn't really help that much. Because if you spend 90% of your query time doing I/O and 10% doing CPU type work, then even if you made just-in-time compilation made the query infinitely faster, you could still at most win 10% of the performance. But if you have individual queries that are I/O bound, but your entire workload also is CPU bound, then even doing just-in-time compilation for the I/O bound queries can help your overall workload, even though it does not reduce the time for the I/O bound query individually that much. And the basic case where it mostly helps is that you have analytics queries that run a long while, because then the additional 200 milliseconds or something to do just-in-time compilation with optimization and inlining just doesn't matter that much. Because if your query runs for 10 seconds, 200 milliseconds, that then make the query run for the rest like 1.8x faster, 2.5x faster, that's very, very cheap. Another case where it helps a lot is if you have relations that are very wide. That is, you have many columns. And especially if the columns are not null, the just-in-time compiled access is a lot faster than if you did access via the normal in-memory accesses. The second aspect of recognizing when it is likely to help is looking at the individual nodes in a query tree. I earlier had explained that if you look at a query plan, you can see that, for example, in this example, the sequential scan takes 8 seconds, and the hash aggregate takes 26 seconds, including the time of the node below. So this one takes 8 seconds, and this one takes 16 seconds. So both of them take a substantial amount of time. But if you compare that to the top-level node, where the sort at the top, which is just ordered by the aggregated columns, it's 26 seconds. So basically, this one itself does not take any time of its own, because all that time is spent inside the hash aggregate, which means this is not a node that itself makes the query run much longer. Yeah. So when I'm talking about specific parts of the query where like specific types of access is inside the query, it's not that if there's a sequential scan, even if it only takes a millisecond, that it's very helpful. It's if a substantial portion of your query is spent in one of the parts of the query that I'm going to list now, then that's likely to help or not help depending on the type of node. If you have sequential scans, then and that is the portion of the query where a substantial amount of time is spent, then you're quite likely to see benefits from just-in-time compilation, especially if you have where clauses. If you don't have any where clauses and only access a single column, and that single column is the first column in the table, then it's possible that you don't see much benefits. But if you access a lot of columns, if you have complex expressions, if you have any where clauses, then you're much more likely to see big benefits. In contrast to that, if you have a lot of index scans, and that includes index-only scans, then it's very unlikely that just-in-time compilation actually helps you, if that's the majority of your time. The reason for that is that for the access inside the index, like looking up in a B tree, the node, most of the time is spent at places where just-in-time compilation has no chance of helping, and the rest of the time is spent in places where we theoretically could improve something, but where we currently don't. So index scans themselves, the index part, does never get faster. If you have an index scan and not an index-only scan, sometimes you can see benefits if you return a lot of rows, because an index scan still has to go to the table and fetch the row, and then that has to, again, do tuple deforming, and that part is still faster with just-in-time compilation. But that really means you have to return a lot of rows. In most cases, that will then yield a bitmap index scan, because that's often faster. So with bitmap index scans, you're a bit more likely to see benefits, because they access a lot of rows, and they have to deform all of those. There's nothing like an index-only scan for bitmap index scans. You often have rechecks. You often have additional quals, where clauses, so that you're more likely to see benefits. The biggest case is really like if you have hash aggregates or group aggregates, because they're typically CPU bound, because the aggregate code itself does not regularly do any disk accesses. It will sometimes do, if you have toasted columns, then it will do disk access. But if you really have not that wide columns, you will see most of the time is doing like invoking the transition function, and deforming the input tuple, and so on. It's worthwhile to note that for group aggregates, that is aggregates that are implemented by getting sorted input and that way identifying the groups, that input groups, you will see benefits from reducing the cost of the transition function, but the sorting itself, as you see in the next point, is actually not accelerated at this point. There's absolutely no intrinsic reason to not make sorting faster. We should really do that, but at the moment, sorting is not accelerated by just-in-time compilation. If you have a lot of joins and the join nodes themselves take up the majority of the time, at the moment, just-in-time compilation is not that helpful. We could make that a bit better, but some of that is pretty intrinsic. If you have an index-nested loop join, it will not get a lot faster because the time itself in the join is not really spent doing expensive things inside various expressions. It's that it has to access an index every time and so on. So that's where the time goes. And so that's just not work that's very amenable to be benefiting from just-in-time compilation. Similarly, with merge joins, we currently don't benefit at all from just-in-time compilation. We could benefit to a bit. Hash joins at the moment get a bit faster because we have to compare the columns afterwards, but we at the moment do not, for example, accelerate the computation of the hash values for the join, and that's actually where most of the time is spent. So that's at the moment not yet accelerated, but we could accelerate that quite a bit.
If you were able to JIT the sort stuff, would that actually make it more likely that Postgres would prefer a merge join with an explicit sort?
Wait 1 or 2 slides. No, at the moment. I said that joins are not likely to benefit, but if you have like columns that are not part of the join, cannot be computed by a merge join, but because you have more complex expressions in there, if you have non-equal parts clauses in the join, those are actually going to benefit from just-in-time compilation. So if you have, for example, have a join on a column and then do like inequals comparison of another column, that inequals part or smaller or bigger or whatever, that is going to benefit from just-in-time compilation. So how can you identify that you are likely to have workloads, a workload where it's helpful to do just-in-time compilation? I think the basic start you do is, hey, I'm a bottleneck by something on the server side. You can check with top or htop or something like that shows you the CPU usage, whether your workload currently has a lot of CPUs that are 100% used. If they're not no CPU, if your system is mostly idle from a CPU usage point of view, you're very unlikely to benefit from just-in-time compilation. In contrast to that, you can check whether you're currently I/O bound. And if you're fully I/O bound, it's also relatively unlikely that you're going to be benefiting from just-in-time compilation that much, if you're not CPU bound. And IOStat can show you. And I think the next thing to check really is, do you have any long-running queries? You might know the answer anyway, but if you don't, you can just check pgstat activity. It has a column that shows you when the query started, and you can just check how long have your queries run. If the answer is yes, or a good portion of my queries take 10 seconds or 3 hours or 3 days, then yeah, it might help. If all your queries are finishing within like milliseconds, you're definitely not going to see benefits from just-in-time compilation. If you have a workload that changes over the day, it can often be useful to look at pgstat statements, which will show you, especially if you enable check I/O timing, whether how much time is spent doing I/O. There's the block read time column, and that will show you how much of the time in total has been spent doing I/O, and how much time has been the query taken in total, and that's the total time. So you can subtract those and see which fraction of the query has done I/O and which then was CPU bound. And then you can look at the queries and see, oh, I can do an explain on the most expensive queries by ordering by total time and see whether they're likely to benefit or not. And if you use explain analyze buffers, like I've had shown examples, if you can see that most of the time is spent doing I/O, unlikely to see benefit, and then you can go through the nodes to see where most of the time is spent and decide that way. So now I'm coming to the problems. What does not yet really work? One thing is that at the moment, the costing about the decision whether to use just-in-time compilation or not is really simplistic. As said, we just check whether the total cost of the query is higher than some specific cutoff, and if so, we do just-in-time compilation. The one problem of that is that it turns out that the effort to do just-in-time compilation is actually not constant. If you have thousands of expressions, super long ones, in your query, the just-in-time compilation takes longer, even though the execution might not be that much benefiting from that. So we don't really take the effort to do just-in-time compilation into account. Another problem is that, to go back to your question, is that at the moment, due to the way the costing works, we do not have a separate costing that says, hey, now that CPU operations are cheaper, it might actually be better to do a sequential scan because we have higher efficiency that way, instead of doing an index scan where we don't see benefits. The reason why we haven't done that is that the alternative would be to basically always have a type of plan where this part of the query does just-in-time compilation, this part does not do just-in-time compilation, and that would increase the total overhead of planning quite substantially. And it's also not necessarily easy to figure out what's the benefit of doing just-in-time compilation versus not doing just-in-time compilation. So at the moment, we don't do that. It might be worthwhile at some later point to do that. It's unclear. Another problem is that if you use the enable _ sequential scan, index scan, whatever gucks that tell the planner to not use, for example, sequential scans, but the planner then actually does end up using a sequential scan anyway because there's no alternative. For example, if you have a table without an index and you do select from that table, if you disable sequential scans, it will still do a sequential scan because there is no other way to execute that query. The way that works is that Postgres just adds a high number to the cost of the query doing that way of querying, and that will then make the plan unattractive. But if there's no other way to execute that query, you still end up with that. And given the way the cost cutoff works, that will mean if you end up with a plan that is disfavored due to enable, we'll just do just-in-time compilation, even though the query might actually be really cheap. So that's not great. Another problem is that if you have bad costing, for example, because your selectivity is totally off, then we might end up doing just-in-time compilation, even if it's not beneficial. I don't think that part is really addressable, personally. I think the problem is there, get to a place where you can have better estimates, but it's a problem, and that's probably one of the riskier aspects of enabling JIT by default is, hey, most of your queries might be faster, but there's one frequent query with bad estimates that turn out to be actually reasonably executable, but now gets slower due to just-in-time compilation. Another problem is that at the moment, the whole query decision is not necessarily the best part, because there might be parts of the query where we do just-in-time compilation unnecessarily. And to anyone who asked that question, it would be a good idea to, for example, do just-in-time compilation more aggressively if you think that the query would be executed multiple times. For example, because you use prepared statements. You could analyze, hey, after 5 times or 10 times of using a prepared statement, I just do just-in-time compilation, because now I know that it will be executed multiple times. But there's a problem. At the moment, you can't reuse the just-in-time compiled functions. Every time you execute a query, we'll redo the whole just-in-time compilation effort. And the reason for that is that at the moment, we don't have any caching infrastructure. And as you can see, the numbers here show it would be pretty beneficial to do just-in-time compilation. There would be some questions whether we wanted to have a cache that is per process, and I think that is probably the most reasonable way. We could have one that's shared between all processes. We could even have one that's stored on disk. But unfortunately, at the moment, it's actually not that easy to do that. The problem is that the way the code is generated for functions, they contain references to local memory that is specific to the single query execution. So you could cache it, but the likelihood of that you execute the query again and that you could get exactly the same memory allocations with the same constants in there is really low. So what we would have to do is to remove all those constants from the code, which actually would have massive benefits, because at the moment those constants in there prevent the LLVM optimizer from making the code faster. I have an experimental branch that removes all those constants, And it turns out the same code otherwise it gets 2.2x faster just by removing all those constants. But there's a lot of infrastructure work to make that doable safely, because if I run the regression tests on my experimental branch, it crashes within a second. So obviously, it's not quite there yet. But that's what I'm working on for PostgreSQL 12, because then will both allow us caching, and the caching then will make it less bad that we make bad decision about when to do just-in-time compilation, because we will pay the price only once at the first execution. So it's not that bad if we waste 100 milliseconds every now and then because of a bad query plan, because the next time you'll just use the cache and it will be fast. One last improvement that I think is really cool, and reusing the graph from earlier, we at the moment do just-in-time compilation and then execute the query. But it would be much more attractive if we didn't have that latency at the beginning, because we lose a substantial portion of the time to do just-in-time compilation. What we could do instead is to start with just do the minimal amount of work to do just-in-time compilation, then start executing the query. And once the just-in-time compilation, which is done in parallel, is finished, then we could switch over to the just-in-time compiled version. And that would reduce the overhead of doing just-in-time compilation at the beginning. And that's not that interesting if you have a workload where the same queries execute over and over and over again, and we have, in the hypothetical world where we have caching, that would be OK. But there's a lot of ad hoc type analysis, or where your queries are super rarely run, like a report that's run every couple days. The caching would likely not help. And for those, doing the JIT compilation in parallel would be quite beneficial. And with that, and we could just do more just-in-time compilation for more things. As I said earlier, we currently don't do the just-in-time compilation for sorting. It would be relatively easy to do. We don't do it for copy input. Parsing the copy input with just-in-time compilation could be quite a bit faster. We just don't do it. And there's more complex products as well. With that, I'm done. Any questions?
How much overhead is memory remapping, because you have to change from random to execute?
It's noticeable. It's usually in the range of 2 to 5 milliseconds. That's on a busy server. It's one of those cases where the smaller your server is, the faster it is. It's actually more expensive if you're large servers. One of the reasons why we make the decision to do just-in-time compilation for the whole query at once instead of doing it incrementally when we discovered that that function is executed multiple times is because that allows us to only do the memory remapping exactly once, because we don't have to, this part of the query is jitted, this part of the query is jitted. That ended up generating way too much remapping. Yeah.
When you're referring to caching for this stuff, would you be caching it like a per query level, or actually caching the tuple deforming, let's say, and sharing that structure or something like that?
I think we want probably a bit of both. I think what we would do is have one level of caching that basically says, in the prepared statements, we say, here's a reference to the exact identifier for the functions. And then we have a second level of caching that says, we need to generate the input program for LVM. And then we have hash that and have a hash table. And that would then be across all functions, across all queries. And that would be then used until you use the prepared statement. So you don't, because otherwise we would not be able to access that cache when the query is executed anew, and not everyone uses prepared statements. And that would then also help with stuff like, hey, let's do reuse the tuple deforming and so on. I mean, the tuple deforming at the moment is optimized for, hey, which columns does the user use? So we couldn't necessarily reuse it all the time. Because we know we're only going to use 3 out of 30 columns, then we can generate a much more compact program than if we used all of them. And it also gets inlined into the expression that actually uses the columns. So the tuple deforming itself is probably not that beneficial, to cache that separately.
As a counterpoint to that, though, for people that are using ORMs and whatnot, you generally see select stars basically all the time. So caching the tuple deforming might actually be relevant there.
But I mean, like if you just do select, like usually those type of query are more like transactional queries, and like if you had that, jitting is more beneficial if you have a lot of aggregates and so on. And there, even the ORM will not have a select star because then the query wouldn't run. So possible, but I don't quite see it. I might be wrong. Yes. Oh, I thought I had a slide. I don't know what happened to that. Yeah, I don't know. Why? Oh, yeah, there we go. I went to the beginning too fast. The Debian packages have it enabled, and it's in the default package. So you just install the beta packages, both from within Debian if you use it like Debian unstable, which you probably shouldn't do in production, and if you install the PGDG packages for PostgreSQL 11, those have it enabled, unless I think you install it on a very old version of Debian that's too old to have a LVM available. So if you have a very old, like if you installed it, I don't know what the oldest supported version, I think it's not Squeeze, but something in that age, it's not supported, but don't do that. For Red Hat, if the yum.postgres.org packages have it available, but it's in a separate package. It's the PostgreSQL 11-LVMJIT. And if you install that, and you can do that after installing the main version of after the rest, then it suddenly is available to do just-in-time compilation. There's docs for it for just-in-time compilation at that URL. If you have problems or interesting notes or something like that, please report them. And I'm more than out of time. Sorry?
I mean, the JIT compilation got interrupted in the middle.
How would it get interrupted?
I mean, is it possible?
At the moment, you can get an error because you like PG terminate backend or something. Then it will get interrupted, but otherwise there's no stop and then redo it or something.
So if you get interrupted, we need to start from the beginning.
Yes, but there's no but in that case you also need to re-execute the entire query. There's no like in the middle of a query restart the query. Postgres doesn't do that at the moment.
Are you asking how responsive it is to interrupts? In other words, once it gets going, how long will it take for Control-C and PSQL to respond? That's the question.
Oh, okay. It will recheck interrupts, but it will only react to terminate like fatal interrupts. At the moment, for implementation reasons, you can't cancel it, so you have to do PG terminate backend rather than PG cancel backend. Otherwise, it will only react to the cancel at the end of just-in-time compilation.
So for the future 12 and forward, what kind of improvements are you working in terms of assessing whether or not this is something that you should be doing with the query? Because right now you have a naive cost cutoff, right? But you could easily extend that based on all the use cases you provided. So that's question one. And as a natural follow-up to that, how long before you think something like this is going to make itself into query planning instead of just execution? Even though I understand the problem's not fairly simple and linear.
At the moment, I personally am not planning to work on the costing part for 12 because I think the caching and the prerequisites for caching are much more crucial. So I think that's what I'm working on. And also I think that's the area where it's unlikely that somebody else has the prerequisite knowledge, where more people have the knowledge to the costing better. You're more than welcome to help. Okay, I think we're done. Lunch.